Hello, my name is Andrew Joy. Thank you all for coming out so early in the morning. My talk is going to be Winning the Race, Multi-Threading and You. So quickly, just a little bit about me. I've been in the games industry about 16 years now, and I've been working in Unreal Engine for about 11 of those years. I mostly do interactive museum exhibit kind of work, so things like big projection spaces where you can interact with the floor and the walls and that kind of thing. And because of that kind of work, it's led me to touch pretty much every part of the engine so far in my time, Unreal Engine specifically. On the side, I also work on an open world survival game, Planetation, as you can see here. And given the genre, open world survival game, it's also led me to touch pretty much every part of the engine. So I'm a bit of a programming generalist at this point. But today I'm here to give a very specific talk about multi-threading. So I'm going to cover three core topics in a moment: thread safety, and then thread pools, and then determinism. But before I get there, I just want to make sure that everyone in the room at least knows what threading is. So I'm just going to quickly cover the basics. So what is threading? Well, in this example, I've split up a CPU into 16 cores. That seems to be about the average nowadays. And let's say we have a single-threaded piece of software writing. Maybe we have Notepad open. We're writing our latest romance novel or whatever you guys use Notepad for. And we're leaving the remaining 15 cores for all of our background tasks. Maybe we have Spotify or Discord or whatnot happening in the background. So this is great for Notepad. And also, I haven't fact-checked that Notepad is single-threaded. Maybe I'm wrong. This is great for Notepad, but let's say we are running a video game. We want to instead spread across and consume as much of the CPU as possible to give ourselves the best performance possible. So we want a video game instead to look like this, leaving just the bare minimum for all of our background tasks. The way that we do this is with threads. So now I'm going to talk about a multi-threaded example, Unreal Engine specifically. Let's say this red thread that's currently running on a single core is our game thread. So this is doing all of our sequential gameplay logic, the standard stuff that I'm sure you guys are all familiar with. Unreal Engine also has a render thread that runs in the background and preps a lot of the heavy-duty work for the GPU. And it also has a physics thread as well as a whole bunch of other threads. If we talk now about my game, it is very heavily multi-threaded because it does a lot of mathematical procedural generation in the background. So if we add my game to this example, we're suddenly using a lot more of the CPU. And my game uses the voxel plugin, which is a very heavily multi-threaded mathematical terrain renderer below our feet. If we add that, we are suddenly up to what we want to be, consuming as much of the CPU as possible. Now, I can't talk about threads without also talking about locks. So if we look at the yellow and the purple, again, that's my game, and the voxel plugin, it's very common that those are going to want to act on the same shared resource, either read or write from it. And if you imagine one really long keyboard with 3 people typing away at it, you're going to get garbage. You're going to get pretty much the same thing if you let multiple threads operate on the same data at any one time. So instead, when we reach those critical sections, we want to identify them. We want to lock that resource so that only one thread can go through at a time. And then we want to relinquish that lock for the next thread. So it would look a little bit like this, with only one thread of each color operating on that data, and then bouncing the lock around again and again and again. So this is great, this secures and safeguards our data, but it can lead to performance problems, and this is also one of the main causes of mistakes, especially to people just getting into multi-threading. So that segues nicely into my first topic, which is thread safety. Thread safety is quite a broad topic, but today specifically I'm going to be talking about the idea of abstracting away the use of locks as much as possible, ideally entirely. So there's a lot of advantages to doing that. Firstly, I'm sure everyone in the room has heard of deadlocks or live locks before. There's a million other bugs that can go wrong with locks. If you add multi-threading, you might spend the next couple months trying to fix very weird bugs, usually around your locks. By abstracting the use of those locks behind thread-safe constructs and types as much as possible, we can just guarantee that we are never responsible for those bugs. We can greatly reduce the number of bugs in our code. Also, these types that we're talking about are battle tested. They've been used in Unreal Engine or C++ standard library for decades and decades. They're written by some of the experts in the field. They're going to be much better than anything you can write in the 20 minutes you have before your deadline. So you're going to get a lot of performance and stability out of this as well. Sometimes they'll even be using lock-free algorithms, so just, no locks at all. So just real quick, this is the format I'm going to use for a lot of the following slides. In white up there, I'm going to demonstrate an Unreal Engine example, but I realize not everyone in the room will be using Unreal Engine. So in red, there will be either a Unity or a C# or a C++ alternative. Where I can't provide one, I guarantee there will be one anyway, because all of these concepts are completely generic. They aren't tied to Unreal Engine at all. There will be a code example as well, but I also want to just quickly mention this is really aimed at beginner and intermediate threaders. If there's any experts in the room, I'm sorry, you'll probably be bored to tears for the rest of the talk. So first I'm going to talk about uint64, and you might see this and think, Andrew, there's no way uint64 isn't thread safe. And I would say most of the time you're right, but there are edge cases where it isn't. So if we look at this uint64 on screen num particles, maybe Chris Murphy has made an awesome new big explosion with 50 billion particles in it. Looks really pretty, but we need a uint64 in order to store this. Funnily enough, that only just bleeds past the first 32 bits because it can store huge numbers. If we are on a 32-bit operating system, this will actually be written as two separate instructions, which gives another thread a chance to come through and intercept it and use, read, or write that data while it's only half written. On a 64-bit system, it can still happen if the uint64 is not on a proper word boundary, like you've done some weird packing or something and you're using it. And both of those are very big edge cases, I know, so you'll probably never run into it. But the general idea here is you can't just take for granted that a type, even a primitive type like this, is going to be thread safe. The only way that you can do that is if it offers a guarantee of thread safety. And the best way to get a guarantee is with atomics. So standard atomic, in this case, if you wrap that around your uint64, that will guarantee that any operations you do to that, read or write, are going to be done in an atomic, thread-safe, single transaction kind of way. They're a lot more complicated than I just let on. So after this slide, if you want to know more, I'd say go to those blog posts. I'm not going to go too into detail about how they work. But in this case, you might also notice I'm using standard atomic. T-atomic, which is the Unreal Engine type, is being deprecated in favor of just using the C++ standard library atomic. So just go ahead and use that. And when you do use it, this is how you would do it. You would load to retrieve the value, or you would store in order to write that value, with a whole bunch of extra parameters that, again, I'm not going to go into. If you don't want to go through those hoops, you can just use it straight like a uint64, so with these overloaded operators, and you can just pretend you're not even using an atomic. This will turn that uint64 or whatever other simple pod type you give it into a thread-safe type that you don't have to worry about and don't have to lock. If we look now at t-shade pointer, we can see a type that is built upon t-atomics. So t-shade pointer uses an atomic under the hood for its reference counting, which makes t-shade pointer by default thread safe. I'll point out that the standard library, C++ standard library shade pointers are not thread safe by default, at least in every case, especially when you're changing what they point to. T-shade pointer provides this optional template parameter here, ESP mode, which lets you opt in or out of thread safety, and by default it is thread safe. I can't really imagine the reason why you would want the extra performance of making it not thread safe. It's not a big overhead, but you can if you want. If you want to see a more complex type that's built upon T-atomics, and again, no locks at all involved here, I will show you TMPSCQ. I want to give you an example of this from our game of how we use it, but I'll do that in a sec. Let me just explain how it works. MPSC, in this case, stands for multiple provider, single consumer. And what that means is, in our case, we can have multiple background threads spinning away, generating all of our landmark data, so things like trees and boulders and cool things you're going to discover. Multiple provider threads, in this case, can be feeding that data into the MPSC queue with no locks, no fancy anything. They barely even know that they're threaded. And then a single consumer, in our case on the game thread, is pulling that data and spawning those actors with the bare minimum of work, again, on the game thread. So I'll give you a quick little demo of this. I'm just going to tab out to our sandbox world. Let me do this. Full screen it. There we go. So this is our sandbox world. I'm just going to run around, use the jetpack a little bit, and find in the distance, you will see, I've taken the dither effect off, so you'll see in a sec, we're getting landmarks popping in. So we have trees, boulders, etc. spawning in chunks that are now becoming relevant to our player. But if you want to see an even cooler example, unfortunately there's a cloud above us now, I'm going to spawn an abandoned bunker. So quickly, these are advanced landmarks that you can find out in the world, and when they spawn, they will generate an abandoned, procedurally generated farm around themselves. So when I do that, you will see it's all popping in over time in a way that doesn't tank our frame rate. So all of this is, again, procedurally generated with maths. Every time you find an abandoned bunker, it will be completely different. We can't just load it from disk. We need to generate it. And that is all done through this MPSC queue. So if I just quickly go back. Okay, so this is how we do it. It's pretty straightforward. We just provide this simple spawn actor queued function. Operates basically the same as spawn actor. That you're familiar with from Unreal Engine, takes a transform, optional parameters. In our case, we can't immediately return the actor that you are spawning because it is happening on these multiple provider background threads. It won't happen straight away. So instead, you can provide a callback that will allow you to do, the initialization later on, or to keep track of it in case you need a reference to it. From there, we do the actual thread stuff. So we increment a standard atomic here. This is for cosmetic purposes only. It's just for tracking the number that we have pending on screen in our debug logs. And then we feed the data into our TMPSC queue. So I will note quickly that these are technically thread-safe operations individually. So one is an atomic, one is built upon atomics, but in sequence, they are not thread-safe because we aren't locking and all of that. A thread can come in midway through and change this. But because our atomic is cosmetic only, we have accepted that risk, it doesn't matter. And because of just the order of operations that we do things on the next slide, we can also guarantee that the atomic will never permanently desync from the actual number stored in our spawn queue. So this is the single consumer on the game thread. We tell it how many seconds or milliseconds that we have left with which to spawn actors on this frame. It happens right at the very end. And if we have spent 15 milliseconds or so on this frame, we might spend maybe 1 millisecond just to keep us above that 60 FPS target threshold. 1 millisecond spawning remaining actors. We begin by figuring out our start and our end time. In this case, it's using date, time, and time span, but in reality, it uses cycle counting. That's just too much to put on screen here, but it is a little bit more performant. From there, we will just loop again and again and again until we run out of time or we run out of actors to spawn from the queue. This is where we protect our cosmetic atomic. We first retrieve from the queue if possible, and if we did manage to retrieve from the queue, we will just decrement that cosmetic atomic. From there, it's just traditional spawning an actor. We spawn it, and then we initialize it with our callback if one was provided. So that was thread safety, and again, the main concept there is abstracting away your use of locks as much as possible. Basically getting rid of any friction that you might end up accidentally causing bugs with. The next topic is very similar, thread pools. We're going to be abstracting away our use of threads as much as possible. First though, how do you make a thread in Unreal Engine? You would use fRunnable thread. You'd inherit from runnable, you'd provide a run function, and that is the lifetime of your thread. When that function returns, that's your thread done. You would then create the thread with fRunnable thread, fire it off, and it would do your work from start to finish. You can do it even simpler using the Unreal Engine async library. Async thread will do all of that work for you. It will create the thread, inject your work, fire it off. You never even know that the thread is there. Or you can use async task. Even simpler, it will inject your work into an existing named thread. If you want that work to run on the game thread, this is how you do it. That's very important if you want to do things like spawning actors that can only be done from the game thread. Or if you want background work, you might run it on the rendering thread or whatever has spare capacity. But let's just say that we're using threads directly and try and use this to illustrate why we should use a thread pool. Let's say we have a piece of work come in. We create a thread, inject the work, fire it off, we're good to go. But then another piece of work comes in. So we create a thread, inject the work, fire it off, but then 3 more pieces of work come in, and suddenly we have a lot of threads. If you remember earlier, we didn't have that many cores left over between what the engine and all of our other software is already using and background software. And if we start using too many threads, we will quickly throttle our CPU if we run over how many cores we have. Our threads will start running like this. The scheduler will come in and stop starting them, giving them all a chance to run. And this is something that we want to avoid. It can be relatively expensive, and it's just inefficient use of threads. Instead, what we should be using in this case is a thread pool. So when you create a thread pool, you give it a certain number of threads, and that's as many threads as it will ever have. From there, you feed it work, and it will take that work and schedule it itself on the next available thread. If you give it more work, it will chuck it on the other available thread when it becomes available. And if there are no available threads, it will just schedule it for you after existing work has been completed again and again and again. In this case, we can make sure that we never have more than 2 threads. We still get the same amount of work done, albeit a little bit slower, but it might end up being faster because we aren't just choking out our CPU with heaps and heaps of threads. A lot of advantages to this. There's no micromanagement. We never accidentally create a thread and never use it or never fire it off or create too many threads. Someone, I'm sure out there, will be running your game with like a 4-core CPU or something atrocious. So you never want to accidentally just create too many threads and assume it'll always be on the best hardware ever. It also limits user error. No like intern can come in and accidentally create 1,000 threads and break your game. It lets us focus on a work-centric approach as well. This is the most important part. Instead of saying, I have this work I want to do, I'm going to create a thread, you would just say, I have this work I want to do, and then feed it to the thread pool, and it will handle how it gets done, where it gets done, more importantly, and also when it gets done. This gives us more performance because creating threads and destroying them has a bit of a cost, a bit of a creation tax, if you will, and again, scheduling problems if we accidentally create too many. So it's just, there's only advantages. This is how you create a thread pool in Unreal Engine. You allocate a default thread pool, or you can customize your own and instantiate that. You would tell it how many threads you want it to operate on and how much memory you want each thread to have, which is another very important value that can cause bugs. From there, your thread pool just exists and you can just feed it work after work after work until you are done. Or you can do this even simpler, again using the async library. Async pool will just let you point your work at a specific thread pool, which is useful because Unreal Engine just provides a global thread pool that you can use as well in case you don't want to be creating your own. I want to give a little honorary mention here to Parallel 4, which isn't technically related, but it is run on top of a thread pool. If you have a really long for loop, like 10,000 elements, and you know each of these iterations is going to be parallelizable, so they don't depend on the previous iterations or anything like that, they're thread safe, you can just feed 10,000 iterations into this Parallel 4. It will spit them out quickly on a background thread pool, out of order, so it might be like 1, 5, 20, 7, etc., all of that, but it will get them done super fast. More modern in Unreal Engine is this UE tasks namespace. It has a whole bunch of just really handy threading helper functions and types. In this case, launch will do exactly what we've just seen. It will take your work and add it to potentially a thread pool or the task graph or whatever else it's using behind the hood, but you don't have to point it at a specific thread pool. Again, just focusing on, I want this work done. Also in UE tasks is this new type fpipe, and I want to quickly talk about this because it's very cool and I've got an example from our game. We begin by creating a pipe just like we did a thread pool earlier, and then we feed it work after work after work just like a thread pool. And it is a thread pool, but it's special because it's a thread pool with only one thread. And you might be thinking, Andrew, that's stupid. But there is a really good reason for this. Basically, we get the benefits of threading without actually doing threading. If we have a thread pipe running off to the side, adjacent to a block of shared resources, a block of data that is either really hard to make thread safe or is just too expensive to make thread safe, we can feed work to that pipe, running it off of the game thread, the benefits of threading. But because that work will be done one after another, sequentially, we don't ever have to make the data that it's operating on thread safe because it will not be accessed, in parallel all at the same time. Unreal Engine uses this for their save game system. That way they don't need to make their file system thread safe. You just feed whatever you want to save or whatever you want to load into the pipe, and it will do the work as quickly as it can on a single background thread and give it back to you. In our case, we use it for our procedural generation background thread. This is Frontier World, which is our procedural generator. Basically, it will provide itself a lot of work as you discover new chunks, but also external actors can provide it work, like the abandoned bunker that you saw earlier. It's pretty simple. You just pass it a work function to execute. We wrap that work in our own account bookkeeping here, which again is just a cosmetic atomic that we increment and decrement to keep track of our work. And then we just feed it all into our pipe. This is the kind of work that we're running on it. Our chunk generator, as new chunks become relevant, like the trees you saw in the distance earlier, we will try and first load that chunk from disk. This happens again on a background thread, so it's a pretty heavy duty task, but if we can't load that chunk from disk, so it's not already been generated, we will just then generate it. Finally, we will populate the chunk with dynamic events that happen every time you discover this chunk again, things like weather events and enemy encounters, that kind of thing. But then at the same time, the abandoned bunker is feeding work into this same thread pipe. This is very important because we want the chunks that are being generated to always have priority. If, for example, a big yawning abyss appears in our world, we want the abandoned bunker to generate around that, so it wouldn't place fences over the top of this yawning abyss. It would neatly put a shed right beside it, maybe, something like that. By doing all of this work in a pipe, we can guarantee that they all happen sequentially, but off of the game thread. And all of the world data that they're using, actors, stuff like that, generally does not have to be made thread safe. Okay, so that was thread pools, talking about abstracting away threading as much as possible. Last, I want to talk about determinism, and this is a bit of a pivot, but I promise you it is very important. I just need to explain first what determinism is. So, in its simplest sense, a deterministic function is a predictable function. If you think of the square function in Unreal or whatever game engine you're using, basically you give it a value, it will square it, give you the value back. If you feed it 2, it will give you a value of 4 back. We know this every time before we call the function because it is predictable. This also makes these functions reproducible. So if we feed it 2, 2, 2, we will get 4, 4, 4 back every single time. Generally, these functions are also thread safe because they are only operating on the inputs that we give them. They don't have a background source of data that they're reading from or mutating, which is very, very important. And finally, because of the fact that they're reproducible and thread safe, they are generally also compartmentalizable, that is a huge word. This is an example from our game. Let's just say this is the entire game world, but really it's just 4 green trees and 3 brown boulders that we're generating here. Our game world, the algorithm that generates our world is entirely math, and it's an entirely one deterministic function. The only input for that function is a single integer seed, meaning, just like Minecraft, if anyone's played it, if you play through a world with a specific seed on your end, and then a friend plays through with that exact same seed number, they will get an identical world from start to finish on their end. That means that our world is predictable, reproducible, thread safe, and compartmentalizable. Even though our algorithm basically stores the entire world in infinite memory, kind of, we can just break it down into chunks and generate individual chunks of that at a time. We know that once we generate further and further and further chunks, they will fit together like a nice snug jigsaw puzzle, and we can just keep breaking it down into small enough chunks to fit into many, many threads at the same time in the background. This is incredibly important for our voxel plugin as well, which I will show you in a moment. So why would we want a deterministic function, or at least a deterministic representation of the world? Well, there's a lot of threading benefits and procedural generation benefits, like I just mentioned. It also feeds into replays. If anyone's, watched a kill cam and you haven't died at the end of it, or your target hasn't died at the end of it, that wasn't a deterministic replay. Unreal Engine replays are deterministic. It also powers some save load systems like XCOM, for example. It's hard to have your character not die. If you reload, you need to do something drastically different. But the one that I really want to point out here is multiplayer. So when we spawn the abandoned bunker in our game, it generates hundreds and hundreds of landmarks around it, right? Fences, all of that kind of thing. We don't want to have to then replicate all of those actors to every single connected client. So instead, what we do is we spawn the abandoned bunker on each connected client with the exact same seed, and it will generate the exact same abandoned farm around it in a reproducible way. It will generate the exact same one that matches the server and matches every other client. This is also how our voxel plugin works. It doesn't transmit the entire landscape data, it regenerates it in a perfectly matching way on every single connected client. How do we do this? We want to remove randomness, or rather remove unpredictability. We still want to keep randomness because it's a procedural game. So let me quickly illustrate how we would do this with srand, the Unreal Engine random number generator. Let's say that we have an array of 10,000 random floats here. We want to populate this array, so we would loop through it in the traditional way, fill it full of random values, and then we're good. We have an array of 10,000 random values. But if we want to run through this loop again and generate the same array of 10,000 random values, we wouldn't be able to, right? Because it's a non-deterministic function. srand gives us a random value every time. Well, it's not actually a non-deterministic function. If we look at how srand works, it begins by taking a global random seed, which is just an integer somewhere, and it mutates it in a predictable way. It multiplies it by a fixed number, and then it adds a fixed number. It then later on uses that global random seed, again in a completely predictable way, to generate the random value that it then returns. That means that if we know what the global random seed is, we can control what value it will return every single time. And also, we can think of it like a pseudo-random number sequence, because 5 values ago, we can predict what the value will be 5 values in the future if we know how this sequence progresses through time. This is how we can hack it in to our earlier example. We can just hard set the seed using srand init to a value that we can predict, like the current index that we're at in our loop. And this will give us a very predictable value from srand. We can populate the same array again and again and again every time. But this is obviously really, really bad. Not only are we getting very low quality random values because the seed is just not changing much, but more importantly, we are contaminating every use of srand for the entire engine henceforth, because we're setting it to a garbage seed value. So really, really bad. Instead, what we should be using is a Halton sequence. And this is a pseudo-random number sequence. You can think of it, again, like a pseudo-random number sequence. You can think of it like an infinite array of numbers, just like the random number sequence we just saw, that extends over into infinity. We can retrieve the 5th value from that array, in quotation marks. We can retrieve the 10th or the 100th as far along as we want. So we can give it the index in this kind of magical array that we want to retrieve. It will treat it like the seed that we saw a moment ago in srand, and it will generate a new random value from it, a predictable random value, where if we pass the same index, we will get the same value. If we want a different value at the same index, we can use a different base. Doesn't matter too much. I just want to point out as well that this Halton sequence has been around since 1964, pretty much unchanged. So it has had staying power. Like I said, these things already exist and they're already really good. We can plug it in here. We can just replace srand like this, and we will get a predictable sequence of random values every single time. More importantly, Halton as a deterministic function is thread safe, so we can plug it instead into a parallel for and greatly improve the performance of our game. I realize this has been a long wind-up about determinism, but I hope you can see why now it unlocks the power of threading at the very least, as well as a whole bunch of other nice little benefits. We can take this a step further and move to a Sobol sequence. Let's say we want, instead of an array of 10,000 floats, we want an array of 10,000 vectors. Maybe we're seeding a field of flowers or trees or whatever, and we need a whole lot of random points. A Sobol sequence works a little bit differently. It takes a complex value like a vector, and it mutates it in a random way. So we would begin with a seed location. This can be hard-coded like this, or rather you would want it to be something like an actor location, for example, the location of the central abandoned bunker in the earlier landmark example. And you would feed it first into Sobol evaluate. That generates the first element in our random sequence. From there, we would skip over the first element and loop through every other element that we want, feeding it into Sobol next, and it would just take the previous value, mutate it, give us back a new random version of it, and then so on and so forth again and again. This is a deterministic function and it is technically thread safe, but I said earlier, not all of them are. This one can't be parallelized because it does require the previous value in order to generate the next value. So a little bit of a downside, and it is more expensive, but the quality of these random values is super good. So, with Halton and Sobol out of the way, I want to give you an example from our game of us using a similar pseudo-random number sequence, but first I need to quickly explain what voxels are. So, I've mentioned voxels a bunch so far. Voxels are basically a way to mathematically describe your world. So, instead of having an artist come into this room and put like a wall over there and a ceiling up there, we would describe that with a mathematical algorithm instead. From there, the voxel system would take our algorithm and sample the shit out of it. It would create heaps and heaps of 3D points in the world in a uniform grid. So we'd have like point here, 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 but also above and down and forwards and backwards. And it would fill this room full of these samples. It would sample every single one of them, determining which ones are empty and which ones are full. So we'd get empty, empty, empty all the way till we're past the wall, and then we would finally get a full. The next step of the voxel algorithm is to determine those transition points and draw a polygon there dynamically. So this, I hope I've illustrated, is a lot of data, a lot of work, really has to be multi-threaded, which means the data that you're feeding into it, the algorithm has to be a deterministic threadable algorithm. This is not reasonable to generate our entire world. Our game, at least, is 100 kilometers by 100 kilometers. That would be nuts. You'd melt your computer. So instead, we only generate a very small part of the world as voxels at any one time, and we represent the entire rest of the world with our atlas. This is a low detail sparse data set that we can just upscale and downscale at will across the network if need be. And in our case, we just store it as simple polygons. The brown here is our mesa biome, which I will show you in a moment. And the blue is our ocean biome. We know if we sample in the brown, we use mesa generation code, and in blue, we would use ocean generation code. As we cross between polygons, we would blend between both generation algorithms, and that's how we generate our whole world into voxels. Again, when we upsample it, we know where each voxel is and what kind of algorithm it then needs to use for that specific biome. Very quickly, the way that we store our own atlas is with Voronoi diagrams. So you can see up there some very pretty colored polygons on screen. That's actually not the Voronoi data. The Voronoi data are those black dots, the sites. You can basically generate all of this data from just those points in space. So it's a very small, sparse data set, ideal for something like an atlas. The way that it works is when you sample the diagram, sorry, the Voronoi, not Voroni, I'm awful at pronouncing it. When you sample in the world, you will only be told which black dot you are currently closest to. So if you sample up in that green, the light green, you would always be told that same black dot that is in that green polygon. As you move closer towards the red, you would be told, oh, you're getting close to the red, close, now you're in the red, and you're suddenly in the red polygon. This is very important. This is how you use it, and you'll see again in a sec. We create an F-Voronoi diagram in Unreal Engine. This simply wraps Voro++, which is a C++ open source Voroni library. So if you need to use this outside of Unreal Engine, you can easily do it yourself. You would generate your own sites in whatever way you do that. We just use a whole bunch of random math. You create your Voroni diagram representation, and then you feed all of your sites into it. The final important step is compute all cells. This translates all of those points into polygon data that we then cache and treat as our biome locations. Finally, every time we need to know which biome we're in, we sample the Voroni diagram with find cell. That tells us which site we're closest to, which we can relate back to a polygon that we have cached, and then we can use that polygon's generation code for our math, for our voxels. Okay. That was a lot of talk about deterministic algorithms. I want to show you how it works now. So this is our mesa biome, all procedurally generated from math. This is millions and millions of voxel samples happening all the time as you move through it, as it unloads previous voxels and generates new ones for you to see. So this is all generated with this code, or at least the code on the next slide. So you're not expected to follow along exactly what it does because it is a lot of math to just throw at you, but I want to illustrate the multiple uses we have of deterministic algorithms that allow us to process millions of these at the same time across many, many, many threads. So this is the ground height function of what you just saw. Again, that biome was basically an American mesa, like a stepped terrace kind of thing. So we want to generate steps and we want to generate terrace fall-offs inside of this code. Our deterministic input here is our atlas sample. So it began life as a location. We sampled the Voroni diagram. We got our polygon data out of it, and we figured out first which biome we are in, which is the code that's being called, but also how close we are to the edges, what other biomes we need to blend with, that kind of thing. The deterministic output here is our voxel float value, which is how full or how empty we are between -1 and 1. We begin by sampling Perlin fractal noise. This is just a more advanced deterministic pseudo-random noise function. We pass in our current sample location. It returns a nice quality noise value, which we then layer over the top with a higher frequency, lower strength noise value to give ourselves kind of a nice bumpy floor. From there, we want to figure out which actual terrace we're on. If we're on the highest or the next or the next, we use a max function, which is very simple, but it is deterministic. That gives us nice, sharp fall-offs, like an actual set of stairs. But we don't want that. We want the ground to look almost like a waterfall flowing over, like a nice, smooth flow down these steps. So we will go back to our original deterministic weight and generate our overflow value from it, using deterministic simple math functions like min, fmod, absolute. Finally, we combine the two with pow and sine, again, very simple functions, and then we add it to our base world height. All of that math generates the ground height for this biome, again, across many, many millions of samples happening all at the same time on our background threads. So that was my talk. We covered thread safety, so abstracting away the use of locks as much as possible. We covered thread pools, so again, same thing with threads, minimize your use of threads, and then determinism. I hope something there helped you. Thank you very much for coming, and I believe we have time for questions. Yeah. Easy. Okay. Well, if anyone has any questions, feel free to grab me any other time throughout the day. I'll be outside for a bit anyway. Thank you very much for coming.